Hello. Today I would like to explain how to solve these four questions about the continuity. Okay, this is part of the calculus stuff under the limit section. Okay, so first question is at what points are the functions continuous? Okay, so you have a given g of x, which is defined in piecewise defined function. For any value x less not equal to 3, it is given by this. And when x is 3, it's defined as 5. Okay. So you want to know this is well-defined function on the interval of negative infinity through positive infinity. And at what point this function is continuous? And at what point this function is not continuous? First things you should know is this rational function is continuous everywhere where it is well defined. So this function is well defined everywhere except possibly at the value of 3, which makes the denominator 0. But that's actually here. So everywhere except 3, it's continuous. Everywhere except 3, it's continuous. Okay. So gx is continuous everywhere, possibly except x is equal to 3. Well, at x is equal to 3, you have to check whether this function is continuous or not. Okay, how do we show this is continuous or not? Okay, so to check the function is continuous at the given point, you have to use the following statement, following definition. Function fx is continuous at x equal to a if the limit of the function as x approaches a is equal to the value of the function at that point. Okay. So in other words, the limit must be equal to the actual value. So in this case, you have to check the limit of the function g as x approaches 3. And you have to check that is equal to the value of g, function g at x equal to 3, which is 5. Okay. So let's check the limit. So the limit of this is, although this is a piecewise defined function, this limit indicates x is approaching 3, which means, more specifically, x is approaching 3, but not taking the actual value of 3. So you are taking any number except 3, so you are using this definition. Okay. So you need to find the limit of this function. And you can check that the denominator is 0 and the numerator is approaching 0 as well. So you can reduce the fraction by factoring. And that is equal to 5, okay? Which is equal to g of 3 in this case, okay? When g is 5, right? So if this is equal to this, right? If this is equal to this, then gx is said to be continuous at x is equal to 3 as well. So here's a conclusion. So from first, this function is continuous everywhere, possibly except x equal to 3. And from this computation, you showed that the function is also continuous at x equal to 3. So together, you can conclude that gx is continuous everywhere. Okay. So the conclusion is gx is continuous on negative infinity through positive infinity. Okay, everywhere. Okay. I'm going to have a similar question next. Same question with this function. Okay. Please note this is just a linear function. Linear function. Linear function is continuous everywhere on the domain. Okay, this is an exponential function. Exponential function grow like this one. This is also continuous function everywhere on the domain. And this is a parabola, and the parabola is also continuous everywhere where it is defined. So again, this function is continuous everywhere below 0. It looks like a line. And it's continuous everywhere between 0 through 1, like this. And it is continuous for any number above 1, like this. Okay. So it's well connected here, and it's well connected here, and well connected here. However, you are not sure whether it is continuous at this point and at this point. Okay. So 2 points to check. Is fx continuous at x equal to 0 and at x equal to 1? Because everywhere else it's continuous. Okay. So let's check this one first. So you have to check the limit of the function as x approaches 0 is equal to the value of f at x equal to 0. However, unlike this one, the limit of this is not easy to do, because left side of 0, you have to rely this rule, but the right side you have to use a different rule. So you have to use left side limit and right side limit to check. So we have to check left side limit first. Okay. So for any number below 0, when x is 0, you may use this rule. So you want to take a limit of this function as x approaches 0, which is 1. Okay. Now I'm going to check a right side limit. Okay. So for any number close to 0 but slightly positive, you can use this rule. Okay. Because you want to take a number close to 0 but above 0, so you always use this rule. So you can rewrite fx as e to the power of x, and this gonna approaches 1. Good. And now, not the left and right, but at the value of 0. So what is f of 0? F of 0 is e to the 0, which is 1. So what this says, so left side limit approaches 1, right side limit approaches 1, and the value at that moment is also 1. So left, right, and that point is all have the same value. Therefore, function fx is continuous at x equal to 0. Good. One more point to check. So now you're going to check. Okay. Now you're going to check whether the function is continuous at x is equal to 1. Okay. Same way. I'm going to check the left side limit, right side limit, and the value at that point. Okay, so left side limit is x approaches 1 from the left side. Okay, slightly less than 1, so you're going to use this rule. So it's going to be the limit of this function as x approaches 1, which is e. Okay, and the right side limit is what? So any number x greater than 1, you have to use this rule. So fx can be replaced by x squared plus 2, because that's the rule you're going to use. And the limit of this is 1 plus 2, which is 3. What does it mean? Okay, now left side limit approaches e, right side limit approaches 3. They are different. So the limit does not exist at x is equal to 1. Does not exist. Which means fx is not continuous at x equal to 1. Okay. So if the limit does not exist, then it's not continuous. Okay. The function is continuous if the limit is equal to the value at that point. But If the limit does not exist, then it's not continuous. Okay, so conclusion. Fx is continuous on everywhere except at 1. So negative infinity through 1, union 1 through infinity. Okay, going to move to the next question. Okay, here's another question, third question. So define h of 2 in a way that extend h of t, function h in terms of t, to be continuous at t is equal to 2. So this function is well defined anywhere outside of t is equal to 2, but it's not defined at t is equal to 2. And we want to extend this function. So this function looks like this. So some kind of graph, but there's no graph at x equal to 2. And we hope to define this function at x equal to 2, so the function become continuous at that moment. So h of t is continuous at that moment if the limit as t approaches 2 is equal to h of 2. Okay, that's this. Okay, this is continuous at t is equal to 2 only if the limit is equal to h of 2. Okay, so we just need to compute the limit. So the limit of this one is what? Okay, this is 0 over 0, so you can reduce the fraction by factoring like this, and reduce the fraction and take a limit, you're gonna get 7. So this must be equal to this, but this is equal to 7. So the conclusion is h of, let's define h of 2 as 7. Okay. What's happening here is this function is basically y is equal to t plus 5, except at t is equal to 2. Okay. And by defining h of 2 as 7, we can fill in the hole, and it makes this function continuous at x equal to 2. Okay, similar question, but the next one, last one. For what value of a and b is this piecewise defined function continuous at every real value x? Okay, let's graph this one. Okay, so function fx is -2 for any value, any x below -1. So when x is -1 or -2 or -3 or less than that, then y value is -2. So graph looks like this. Okay. And for any x above 1 or equal to 1, the y is 3. So f of 1 is 3, f of 2 is 3, f of 3 is 3, f of 4 is 3. Any value above 1, the y value is 3. This is 3. Okay. And for any value between -1 and +1, it is some kind of a linear function. It's a first degree function, polynomial, so it's a line. And we want to make this function continuous everywhere. So basically, we want to make it well-connected function, well-connected graph. So if we want a function looks like this. Okay. Well, how do we solve this one? So from this function f is continuous everywhere below -1, and function is continuous between -1 and +1, and function f is continuous everywhere above 1. But we are not sure whether this is continuous or not at x equal to -1 and at x is equal to 1. So we need to make fx continuous at x is equal to -1 and at x equal to 1. Okay? Then it's become continuous everywhere. So we just need to check those 2 points. So function f is continuous at x equal to -1 using this. Means the limit of x approaches -1 of fx is equal to f of -1. And likewise, this one is x approaches 1 of fx must be equal to f of 1. Okay, now limit of this is what? Okay, so the limit of this one, because any number below -1, you have to use this rule, and any number above -1 but close to -1, you have to use this rule. So you have to split into left limit and right limit, like we did it here. So we wanna check negative side limit, and we wanna have a right side limit, and that's must equal to the value at that moment. Okay, the left side limit is, well, -2, -2, so it must be -2. The right side limit is it's well continuous function. When continued functions, you just take a limit of this function, so it becomes -a minus b. And f of -1 is you plug in -1, so you have to use this rule, so it becomes -2. So from here, -a and minus b must equal to -2. That's the rule. Okay. Likewise, here you have to split into left side limit and the right side limit and the value at that moment. So right side limit, you are using this rule, so it's immediate. You can get it's become 3. F of 1, you just plug in 1, which you have to use this rule, so it is 3. Left side limit, when you plug in x approaches 1, but x is below 1, you have to use this rule. So you are taking the limit of this function, and you just plug in to get a minus b. So a minus b must be equal to 3, and which must be equal to 3. So a minus b must be 3. Okay. So these two must be met. These two equations must be satisfied in order to be in order to make this function continuous at these 2 points. Okay. Solve this, you will get a is equal to I don't know. A is equal to what? Minus 5 over 2. And b is equal to 2 negative 1/2. Yeah, yeah, something like that. Well, I'm going to check by graphing. This point is -1, -2, and this point is 1 and 3. So the slope is 5 over 2. Yeah, so that's the answer. So key idea is basically 2 things. If you want to check function is continuous at one given point, use this rule. If you want to show the function is continuous on some given intervals, basically you can assume the function is well defined and well continuous on any function is continuous everywhere. Well, it is well defined. Okay, so for example, this is continuous everywhere except 3. This is continuous everywhere. This is continuous everywhere, and this is continuous everywhere except when the denominator becomes 2. Okay. So, and when the function is piecewise defined, these points that where the definition changes, these points we have to check the function is continuous or not by taking the left limit, right limit, and the value at that point. If those 3 are equal, it's continuous. If any one of them is different, it's not continuous at that point. Okay. Okay, so that's it for today. Thank you for listening to the lecture.